This is 8.1 Preliminary Theory of the Linear Systems. Or a compact way of writing this, where you can see the parts. This is x prime, a column vector. This is A. This is x plus my f. Yeah, we're missing the x here, so we give that a 0. We're missing the y here, so we give the middle one a 0, assuming it's x, y, z. So basically, this is our solution, and we're going to plug it into our dE right there. So same old, same old. So just multiplying this out. Well, you can't add this any further. Just change that to minus. So now we can take the derivative and plug it in. Simplify this one more time. Add these two, and then these two. So we're going to plug in here. Whoops. Oh, here's our dE, sorry. So that's where we're going to plug in. We're going to plug in here and here into that dE. So x prime we write on the left. And then plug x in on the right. And then we got to show these sides are equal. So the left is already simplified. So we're going to multiply this right side. Let's remember though, this is a 2 by 1. Because we're adding, this is one row. Here is a 2 by 2. And this is a 2 by 1. When you multiply 2 by 1, we will get a 2 by 1. We multiply this times that row for first row. And then my second row is this row times that row. So just minus 1 times that first row. And plus 0 times the second row, which will 0 out. Add our like terms. And it looks like we got the same. Both sides are equal, so therefore it's a true statement. So if you recall, if we have all these individual solutions, if we write a linear combination of them, well then that x, that's the linear combination of all the solutions, is also a solution. And that's because we've learned about this already. It's the superposition principle. So our definition of dependent is if there exist C1 through Cn that are all not zero, such that the linear combination is equal to zero. And what this is really just saying, if this is true, basically one of them can be written in terms of the other. One term can be written. So otherwise it's linearly independent. Another definition, the Wronskian. So let's say all these x's are column vectors. And there are basically, let these be n solution vectors. The Wronskian, so if you have a set of n solutions, column vectors, they are independent if and only if, let me write that a little bit neater. The Wronskian of these vectors. So before we did the Wronskian as functions, they're vectors now. Independent if it's not equals to zero. Kind of the same definition as before, but before they were functions. Now they're solutions to the differential equation. So it's the fundamental set of solutions for this differential equation. Let's look at an example. So we are assuming that these are solutions. We're looking to see if they're a set of independent solutions. And then this really gets multiplied in there. So we can also, property of determinants, we can factor out that. We can factor out that e to the 3t. That, you add the exponents, and then we can times, just pick this row, 1 times the determinant of that minor, and then this minor, it's got to be minus 1, and the last, and then working this out. So taking this last determinant, 6 times -1 is -6. 3 negatives is actually -26. And we know that's not going to ever equal to 0 because it has an asymptote at 0 and it's above 0. Well, in this case, it's negative below 0. Therefore, independent bases. So xp is going to be a particular solution to the linear x prime equals ax plus f. And then xc is our general solution to the homogeneous. And our homogeneous is just x prime equals a x without the f. I'll do one quick example. So here's our dE. We're going to verify that xp equals this one is a solution to this dE, and this is a non-homogeneous. Of course, xp, like we just said, is a particular solution to the non-homogeneous. This is non-homogeneous. So again, here's my x, p. We're going to find x p prime and then plug it in there to our dE here and here. So we take the derivative of each one. Pretty simple derivative. And now we plug it in. So we replace x prime with this on the left. And now let's, there's nothing to do on the left. So we're going to multiply these, distribute that, add them up, and see if we get that value on the left. So we're working on the right-hand side. So again, this is 3 by 3, 3 by 1. We do get a 3 by 1 plus a 3 by 1. That's my first row. The inner product of that. My second row. And my third row. Yeah, and the other two terms are 0 just like that. And then we just have to add them up. Yeah, I just copied that wrong. And I actually copied this wrong. So that's a positive 1. So that's positive 1. Positive. Because that was a positive 1. And they are the same. Therefore, XP is a solution. And that's it for this section.